Hi, welcome to our lecture on ordinary differential equations. Today we are going to talk about the last case we had left for solving systems of equations where our parameter lands us on the so-called TD parabola. Let me go ahead and explain the situation. So you remember we had systems of equations. We solved many different cases. So long as we had two eigenvalues, it was easy to follow the method and get our answer. What we want to do today is to look at the situations where the eigenvalues become the same. We said when the eigenvalues are the same, one of two extreme cases is going to happen. One is that every vector becomes an eigenvector. That means our matrix is just a multiple of the identity. The other extreme is that one of our eigenvectors goes missing and we just have one eigenvector left. This becomes a rather complicated case to consider, and we are going to try to explain it by going to some items we did at the very beginning of the semester during our review, and then come back and give some flavor to that method, that formula that we had, explain it in certain number of ways. So I'm going to have a list of 4 methods for dealing with the problem that we are facing right now. One is the ready-made formula we had at the beginning of a semester. We are going to fall back onto that position because it's the easiest way to approach the problem. I'm going to talk about the method of reduction. I'm going to talk about the splitting method. And item number 4, this generalized eigenvectors. We are going to leave it out from this lecture, but if you go to some major textbooks, you are going to see that method explained in detail. So let's go to very beginning of semester. We had second order equation like the equation I have here. You remember the solution step where it was very straightforward. R squared plus 10r plus 24 equal to 0. That was our characteristic equation. We go ahead and factor it. That is not an eventful situation. We get two numbers, they are distinct, and that gives us our answer. Y is equal to some number times exponential of minus 40, some number times exponential of minus 60. So that was easy enough. Now we look at the following rather puzzling situation. In the second equation, all that I have done, instead of 24, I have 25. And what happens is that our factors become the same. So our roots become the same. We gave a special name to this thing, call it a pair, or identical roots, or root of multiplicity 2, or some such designation. The problem is that we can no longer write, so let me put a cross on it before I even write it. So we cannot just write exponential of minus 5t and exponential of minus 5t. These are same functions, and you can just factor it and write a plus b times exponential of minus 5t. We are missing our second entry. So that's not going to give us the correct answer. At that point we said, well, simple solution here is a recipe. We just gave the recipe and we said we have y is equal to exponential of minus 40, and then second function you have to multiply it by minus 5t. Now these two functions are so-called linearly independent from each other. They are not a constant multiple of each other. So that becomes the solution that we have. So if the equation that we had identical root, we have a ready-made recipe, and that is what's going to be our fallback position for quick solution without getting ourselves in lengthy processes. But we want to go ahead and explain where did this t come from and how does that work for us in the case when we are on this parabola. Okay, to explain this, of course So the ready-made formula means you take this thing and plug it back in your equation. You see that it is actually a solution, so somebody else has found it for you. But how about going a little bit deeper than that and trying to figure out how do we resolve this problem in similar situation elsewhere? So next easiest thing to look at is the method of reduction. Method of reduction, we say, okay, we have one solution that we are sure of, which is exponential of minus 5t. That one we have no problem with. Second solution, I will write it just as y. We are going to take it to be a multiple of the first solution, exponential of minus 5t times some function v, which we don't know as yet. V is some function of t. We are to find that out. It's always a safe bet to say that y is, you can simply define v as y times exponential of 5t, and then see what can you get for v. So what we are going to do in the method of reduction, we take this, take its derivative, plug it back in our equation, and try to figure out what v should be. So I go ahead and take a derivative of this. You carefully apply the chain rule. So you have minus 5 exponential of minus 5t v, and then exponential of minus 5t v prime. We have to do this second round. So y double prime, I take a derivative, becomes 25 exponential of minus 5t v, and then the derivative of the second term is going to be minus 5 exponential of minus 5t v prime, exponential of the derivative of the second term. First term, just like the previous case, is going to be minus 5 exponential of minus 5t v prime, and finally derivative of v prime, that's going to be v double prime. Let's simplify a little bit. What happens, always happens, that these two are the same, so it doubles up. 25 exponential of minus 5t v minus 10 exponential of minus 5t v prime, and exponential of minus 5t v double prime. We take these things and combine them. How do we combine them? However, we want them here. We want 1y double prime, we want 10 of y prime, and we want 25 of y itself. So let's combine these things and see what we get. So if I have 1y double prime and 10y prime and 25y, I get all of this, which is 25 exponential of minus 5t v minus 10 exponential of minus 5t v prime plus exponential of minus 5t v double prime. So that is one term. 10 of y prime term, 10 of this, so we have to take all of that, multiply by exponential of minus 5 exponential of minus 5t. It would have been smarter to factor the exponential, which is showing everywhere, but that's fine, we go ahead. Exponential of minus 5t v prime, and finally we have 25 of the first term, 25 exponential of minus 5t v. All of that, if this wants to be a solution of this equation, has to be equal to 0. Okay, now what? Well, now quite a bit of simplification is going to happen. Let's indicate it. So I have minus 10 here, and here's plus 10. They cancel each other out. I have 25 exponential of minus 5t times v, and then I have minus 50 here, and again plus 25 here. Plus 25 minus 50 plus 25 cancel out, so a lot of magical cancellation. All that is left here is exponential of minus 5t v double prime equal to 0. Well, exponential is not 0, so we can divide by that, and we get v double prime equal to 0. So second derivative of a function is 0. That function has to be a linear function. first you recover your first derivative, and the derivative of 0 is just a constant. You recover the function itself, and the derivative of a constant is that times t plus some other constant b. So we have found our v. Our v is the item that is supposed to multiply with the exponential of minus 5t. So I'd say therefore y, which was exponential of minus 5t times v, so it's going to be exponential of minus 5t times at plus b, which if you multiply it out is a exponential of, or let's write it in order of significance, exponential of t, at exponential of minus 5t, and b exponential of minus 5t. Now when you look at that, you see our two solutions. One is what we knew from beginning, exponential of minus 5t, we had that. What is the fruit of our labor here is this new function, t times exponential of minus 5t. And this is the appearance of that mystery t that we had at the beginning of the semester. We just gave a recipe that there is a factor of t that needs to be used when you have identical roots for your characteristic equation. You need a factor of t. So this was the method of reduction. Method of reduction can be expanded and be used in other situations, especially when you have one solution of a differential equation. You can use this to reduce the order of your equation. That's why it's called method of reduction. You reduce your order and then you find your solutions. So that way we explain where does this number t come from. Now we are going to go to the next step. Next step is called splitting method, or sometimes referred to by other terminology. The idea is that when you have things showing up that are identical, try to separate them. How can we separate them? You separate them by modifying your equation slightly. Like instead of 25 we had 24, our roots would have been different and we could have used that formula. So the trick we are going to apply is to take our equation, modify it a little bit, like by an epsilon, get our solution, and then let epsilon go to 0 and see what we get. So let me explain again. So we have an equation which is giving us a bit of a hard time because it has identical roots, and our standard recipe that we had before doesn't work for identical roots. They have to be different. Well, how can we make them different? Play with the problem, play with the numbers that are in the problem until they become different. Just change the things slightly by an epsilon and such until they become different. Get your answers and then let that change you made go towards 0 and see what you get. So we are going to go after method of splitting. It's going to be a little bit lengthier than what we have right now, so be ready that we have a bit more algebra coming up. So splitting method. So in this case we are going to take our equation. We said we are going to change it by a tiny bit, and you have a leeway as to what you want to change. I am going to make a change that's going to be easy on us in terms of algebra. So I'm going to write this equation again. I have r squared plus 10r, excuse me, sorry, of course that's not our equation. To start from beginning, y double prime plus 10y prime plus 25y. That is what I want to solve. I want to remove the appearance of this identical pair here. and that either I have to change this number or this number or this number. All of them lead same place. Easiest one is to play with 25. So what I'm going to do is a nearby equation. So, okay, I have y double prime plus 10y prime. I don't go all the way from 25 to 24, rather I make a small change. And the change I make, for example, I subtract epsilon out of this thing because I want to let epsilon to go to 0. Now our algebra is going to be a little bit easier on us, and we are going to have a little bit of softer landing if I just write epsilon square, because later on I have to take square root when I'm doing quadratic equations such. When I put epsilon square here, our life is going to be a little bit easier, but it's essentially the same either way. So, well, what's the characteristic equation of this one? R squared plus 10r plus 25 minus epsilon squared. How do I solve that? I can solve by quadratic formula, or to be faster, let's say this is r plus 5 squared minus epsilon squared. So r plus 5 squared is equal to epsilon squared. So r plus 5, I take square root, and now that reason I put that square over there is so that here I don't have to write square root. So my r becomes minus 5 plus and minus epsilon. So depending on how big epsilon is, I am splitting, again there's a reason for this terminology I'm using, I'm splitting these things, moving them, so pushing them apart from each other so that there's a gap between the two of them. So one of these things is minus 5 minus epsilon, the other one is minus 5 plus epsilon, and there is a gap. There's a gap between these two. I can go ahead and write my equation as y is equal to my solution as exponential of minus 5 plus epsilon. That's like root number 1, and b exponential of minus 5 minus epsilon t. That's the second solution. Now we shouldn't rush into saying, well, let epsilon go to 0. If I said let epsilon to go to 0, all I get is minus 5t again and minus 5t again. That doesn't solve my problem. Those are identical functions. I cannot use them as two independent functions. So what is the solution then? The solution here is to go after initial value problem. That is, we still need to go ahead and assign initial values. So remember that y of 0 is some number, y prime of 0 is some number, and based on that we can designate what a and b are going to be, and then our solution is going to be unique, and we can actually go ahead and let epsilon to go 0 at that point and actually get a useful answer. So I go ahead and take a derivative of this derivative, so it's going to be a times minus 5 plus epsilon exponential of minus 5 plus epsilon t, and then b times minus 5 minus epsilon exponential of minus 5 minus epsilon t. So what do I expect out of this? I expect that at time 0, value of the function to be little a and value of its derivative to be little b. So what are these things? Well, what is y at time 0? If I put 0 in this exponent, well, the exponent becomes 0 and the exponential just becomes 1. All I get back are the coefficients. So this is nicely enough a plus b, which we said we want it to be some number a. Same story with y prime 0. Y prime 0 is a little bit more crowded. Exponentials become 1 again, but what is left is this one and that one. So I have a times minus 5 plus epsilon and plus b times minus 5 minus epsilon, and I want this to be b. So from this pair of equations, we want to go ahead and find what is capital A, what's capital B, put it back into our equation, and then we have our almost nearly final answer. Well, how do we solve this? Rather easy. Let me rewrite it and clean it up. This is a plus b is equal to little a. From the second equation, I can factor a minus 5 times a plus b, and factor an epsilon times what I'm left with a minus b. That has to be b. So of course the first equation says a plus b is little a. Since a plus b is just a, I put it here and move everything to the other side. So it's epsilon times a minus b, and this becomes a plus, b plus 5a. Is that right? So a plus b was little a. I put it here, moved it to the other side, and that's what I have. Now let me do another thing. I divide by epsilon, so this epsilon comes, this was b plus 5a. I moved the epsilon also to the right hand side. I don't need my parentheses anymore, so let's get rid of the parentheses. So my equation became a lot easier. Well, what is a? I add these two and divide by 2. Is that right? So I'll have to divide by 2 the sum of these two, a plus b plus 5a over epsilon. How about b? Well, I subtract these two and divide by 2, so I'll have 1/2 of a minus b plus 5a over epsilon. So I understand it's a little bit more algebra than what we are used to, and that's why we left this as the last item. So however you want to go after this creature, there is a price to be paid. So this is the price. We are paying it this way. All the items were available to us, and we can go after the problem like this. So y, so this y, just go ahead and write it. My capital A became 1/2 of a plus b plus 5a divided by epsilon exponential of minus 5 plus epsilon t, and then again 1/2 of a minus b plus 5a over epsilon exponential of minus 5 minus epsilon t. Okay, that was our milestone number 1. We have made we split the problem. We put the epsilon, so let's see what happened. We took that equation, it was giving us a headache. We take the 25, change it slightly. I said I put epsilon squared, so avoid writing square root. Imagine having square root everywhere after this. So I put the epsilon squared so that our life is a little bit easier. We solve that equation, we get 2 different roots. So I can apply ready-made recipe that we had. Next, to go further, I have to have initial value problem. I assign the initial value of a function and its derivative, and then go through enforcing of these, and I come to this answer. Now I am ready. Say let epsilon go to 0. So now your calculus skills come in. Let epsilon go to 0 and see what is left out of this. Let me reduce the clutter so that we can actually handle the problem. So what I'm going to do is going to take these a's aside. So I'm going to say y is 1/2 of, let's factor the a as well, a over half of, this is exponential of minus 5 plus epsilon t, and the other one is exponential of minus 5 minus epsilon t. So I'm putting similar things next to each other. Why? Because it's quite obvious what's going to happen to this when epsilon goes to 0. These two terms become the same, becomes twice exponential of minus 5t, and 2's cancel, and I'll have a times exponential of minus 5t. So the fate of this is clear. It's going to turn out into exponential of minus 5t. Is that right? Once again, when epsilon goes to 0, I have exponential of minus 5t, and the same thing again here, so it becomes 2 of that. 2 cancels this 2, and I have just a times exponential. So as epsilon goes to 0, that's what's going to be left here. Next, I'm going to attack this portion. So that's going to be, I'm going to write plus b plus 5a over epsilon. Now I have exponential of minus 5 plus epsilon t, and now this one is subtracted. That's important. Exponential of minus 5 minus epsilon t. Let me reduce the clutter again. I have an exponential of minus 5t in both of these things. Let me put that aside. So b exponential of I forgot one thing. There was a factor of 2 here as well. I forgot that. Let's put it back here. So it was 2 epsilon. b plus 5a over 2 epsilon. I factor exponential of minus 5t, which is common to both of these things, just to make things stand out. I'm left with exponential of t and minus exponential of minus epsilon t. Now let's put the fixed items one side and the ones that are going to participate in the limit somewhere else. So b plus 5a exponential of minus 5t, these are all fixed here, and what is changing is epsilon t minus exponential of epsilon minus epsilon t divided by 2 epsilon. So the question now is, what is the limit of this expression as epsilon goes to 0? What is that going to be? So let's see if you remember your calculus 1 skill, how to take a limit of an expression when a variable goes to 0. You had a variety of tools there. Perhaps the most famous was the so-called L'Hopital rule, or perhaps you have some other ways of going this. Now the letter epsilon might throw you off a little bit because it's not like a letter that you use constantly in calculus. Let me use some other letter. What if you had exponential of xt minus exponential of minus xt divided by 2x? So all over the place, instead of epsilon I put an x. That's what holy letters, so we are familiar with that. Limit of this thing as x goes to 0. What is that? Well, L'Hopital says take a derivative of numerator, take a derivative of denominator with respect to your variable term. So variable term is x here. When I take a derivative, by chain rule a factor of t comes in front, t exponential of xt, and another t, really minus t, comes up front. It becomes another t exponential of minus xt. Denominator, derivative with respect to x, is a 2. What is the limit of that as x goes to 0? When x goes to 0, these exponentials become 1. It becomes 2t divided by 2. That's just t. So limit of this expression as epsilon goes to 0 is t. And that is the t we were trying to justify at the beginning of the semester. Where does this mysterious t come from? So here was a rather long-handed way of recovering that. So let's see what is our final answer. Our first piece became exponential of minus 5t, and the second one is b plus 5a, that expression became t times exponential of minus 5t. So this becomes a justification why the solutions are, well, this one we were familiar with. This is a new creature that has a factor of t in it. Okay, we did quite a bit of algebra here to get to this, but let's see what was the main idea. The main idea is that if you have two identical items showing up in your problem, and because of that you're losing the basis for the expansion that you had, take these, trace them back where they come from. Well, they come from certain coefficients. Modify one of those coefficients, whatever you wish. It's all the same, whatever is comfortable. You have like 3 numbers here, just modify one of them, or even more, and then let the small modification that you make be represented by an epsilon or something like that, and at the end you want to let that epsilon to go to 0. Notice that we had to do some small modification or approach. I had to get the full solution. That is, I had to apply the initial conditions, and then I had a complete solution to the initial value problem. Then I let the epsilon to go to 0, and I see that factor of t emerging out of this limit process. Okay, I hope you followed that, and perhaps you want to repeat it whenever you have time to repeat this process to make sure what you understood. Once again, if you are pressed for time and you want to solve it, well, yes, we have this ready-made formula, we can apply it, but we want to go a level beyond that. We want to learn how to investigate this kind of issues if they show up somewhere else. So we showed so far 2 methods. One was the method of reduction, which is applicable to these kind of problems in ordinary differential equations, and then we showed the splitting method. Now, generalized eigenvectors is going to take a couple of extra lectures to get there to solve this problem, but let me go ahead and just take a system of differential equation, see how we handle it in that case. So suppose we had a problem where x prime is, say, 4x plus, say, y, and the y prime is 4y. Say we want to solve this. Okay, you might say, well, we have done a dozen of these things. How is that any different? Well, let's go see. I have a matrix which is 4, 1, 0, 4. So I go try to find the eigenvalues. 4 minus lambda, 1, 0, 4 minus lambda, and I calculate the determinant of this. The determinant is 4 minus lambda. These two times each other, these two, it becomes 0. And what's the problem now? So we have lambda is equal to 4 and lambda 2 is equal to 4. So when I want to figure out the eigenvectors, 4 is same as 4. When you put it back into this matrix, you get what? 0, 1, 0, 0. Okay, so you take the lambda, put it in this equation, and then you are trying to find the eigenvector of it, so times x, y, and you want to get 0 out of this. It was a rather confusing equation, but let's just write it. This was the first equation says y equal to 0, second equation just 0 is equal to 0. So what do we get out of it? Well, obviously I get y equal to 0. How about x? Well, x is arbitrary. Anything will be fine so long as it's not 0. Well, let's choose some specific one that's going to work for us, a number convenient other than 0. Well, the number is 1 or any number you wish, I got my eigenvector. So I have my eigenvector is 1 0 corresponding to eigenvalue 4. Now you want to say this 4 or you want to say that 4, all I got is one eigenvector, and that is the problem. We have only one eigenvector. How about v2? v2 goes missing. No, there is no v2. That's the challenge. What do we do in this case? So as a matter of practicality, I would say take this kind of equation, and when you're pressed for time, the safest, the fastest way is to reduce it to a equation, to a single equation, second order, and apply the method that we learned there. So safest, fastest way, least confusing to get to the answer is to take it, convert it to a single ODE of second order, and apply that ready-made formula we already had. So that is step 1. Step 2, we can apply the method of splitting. That is, just like what we did here, we can go ahead, modify the entries of this matrix. Any of these 4 numbers will do. If I modify it until the lambdas wouldn't be the same, if lambdas are different, then I have a ready-made solution. I can go ahead and apply that. Again, is the trajectory of the solution is going to be rather lengthy. So let's see. We want to go ahead and so what to do with the second missing eigenvector? Our solution was always xy some number times exponential of lambda 1t times the first eigenvector, and the b exponential of lambda 2t times the second eigenvector. And I just don't have any. I have no there is no such thing. There is no such thing. So we have to go to plan B, and the easiest plan B, as I said, is to take this problem and convert it to a problem with second order. So how do we do that? Let's write. I have x prime is equal to 4x plus y, y prime is equal to 4y. For example, you can take this equation, write it as, take a derivative of it, 4x prime plus y prime. Well, y prime is 4y, and y is x prime minus 4x, or however you do this thing, you come out of it correctly. So I'll have x double prime is equal to 4x excuse me, this was 4x prime, 4x prime plus 4x prime minus 16x. So x double prime, let's bring it minus 8x prime plus 16x equal to 0. So our characteristic equation, r squared minus 8r plus 16 equal to 0. My roots are 4 and 4. So my x is going to be a exponential of 4t plus, now well, you want to maybe pause this thing for a second and answer me, plus what? Plus b, what's that now? Yes, I need a t here. Okay, that I got my x easy without too much pain. How about y? Well, it's the best thing to do. Take this thing, plug it back here, and get your y out of that. So I say y according to first equation is x prime minus 4x. If I just plug it in, I don't need to solve any equation or anything. I just take a derivative of what I had. The derivative of this is 4a exponential of 4t plus, now you have to apply product rule. Derivative of t is just 1 exponential of 4t plus 4bt exponential of 4t. Now minus 4x minus 4a exponential of 4t minus 4bt exponential of 4t. Well, pause it for a moment and say it looks like there are a lot of cancellation here. I am canceling this, and this is canceling that, and all that is left for me is y is equal to b exponential of 4t. So let's see, what did we have? We have x is equal to a exponential of 4t plus bt exponential of 4t, and then y is b exponential of 4t. There are various ways of writing this thing as a sum of two vectors. One of those vectors is our just eigenvector that we had at the beginning, and the other one is going to be a so-called generalized eigenvector. So the generalized eigenvector shows up, but we didn't talk about that in the context of our linear algebra. So this is our solution. So if we come across points on that parabola, so if we have a point on the parabola, one of two things is going to happen. Either your system is multiple of identity. Multiple of identity means something like that. Suppose you have x prime is equal to 3x and y prime is also equal to 3y. Well, what's the solution here? Solution here, x is some multiple of exponential of 3t, and y is some other multiple of 3t. That's probably the easiest one to solve. There's no every vector becomes an eigenvector, and then you write your solution as, if you want, 1 0 exponential of 3t. If you want to insist on writing in vector notation, you have something like this. So this is for a minority of situations where your matrix is a multiple of identity. But if you were at a certain point and your matrix looked like one of these or some other matrices, that when you solve you get two identical eigenvalues, your best bet, simplest, fastest way to approach this problem right now is to convert it to a second order equation, apply the ready-made solution that we had, and then you are all done. Second method, if you want to go splitting method, I'm going to leave this thing to you guys to do, is take that matrix that we have. This was a 0 entry here. You want to change this thing so that your identical roots become two nearby numbers. So what you do is you change it to 4 1 4. Again, you have many choices. Perhaps the easiest one is to have that 0 replaced by, again, epsilon squared to make our life easy. So in this case, if you want to go ahead and then form your eigenvalues, so you say the determinant of this equal to 0, you will have 4 minus lambda squared minus epsilon squared. So out of this you get 4 minus lambda is equal to plus or minus epsilon. So lambda becomes 4 plus or minus epsilon. You can continue this and get your solution. Again, it's going to be a little bit of algebra, keeping everything in order. You have to go all the way to bottom of the problem to get your x and y. I recommend that you finish this problem, but again, if you have to do the problem in a short amount of time, the safest, fastest way is what we did. So let's go back to see what happened. We reviewed the formula from the beginning of the semester. Something else we had mentioned at the beginning, but now we are making use of it to see how to handle identical roots. We mentioned a splitting method. That's perhaps the most substantial thing we talked about today in terms of what to do with identical numbers. And there's a way of packaging all of this thing in a concise way in linear algebra that requires so-called generalized eigenvectors, which we postpone. Okay, I hope you enjoyed this lecture. Hope you have a good vacation. Until next time, good luck and God bless.